Hello all, welcome to the first video on section 3.1, an introduction to determinants. Previously we've seen that if A is a 2 by 2 matrix, we've defined the determinant to be the product AD minus BC, the diagonal terms minus the product of the anti-diagonal terms. And this number has a nice property that it completely determines whether or not A is invertible. If the determinant is 0, A is non-invertible. If the determinant is non-zero, then A is invertible. And whatsoever the inverse somehow depends on this determinant. What we would like is a number like this that works for a general n by n matrix. And what we're going to do is we'll walk through the 3 by 3 case first, as they sort of work up to the n by n case. Sure. So let's see here. For the 3 by 3 case, if our matrix A is this one here, A, B, C, D, E, F, G, H, I, then the determinant is going to be what? It's going to look like a bit of a mess for a sec, but that's life. It's going to be the value A times the determinant of what matrix? It's the little 2 by 2 matrix that we get if we eliminate the row and column that A lives in. So it'll be E, F, H, I minus B times the determinant. And we do the same thing. We remove the row and column that B lives in. We get 4 terms that make up a 2 by 2 matrix, and we'll do the determinant of that. So this is D, G, F, I, and then plus C times the determinant of, you guessed it, the 2 by 2 matrix we get by eliminating the row and column that C lives in. So D, G, E, H. D, E, sorry, G, H. D, E, G, H. Okay. And then if we wanted to make this even more explicit, we could say this is A times EI minus FH minus B times DI minus FH plus C times DH minus EG. Okay. And the textbook shows us where this comes from just by row reducing, the matrix, row reducing, A, B, C, D, E, F, G, H, I, 1, 0, 0, 0, 1, 0, 0, 0, 1. Last time we saw if we row reduce the left-hand side here to be the identity matrix, then we get the inverse on the other side. And in the process, we'll pick up this terrible looking number, which is going to control whether or not we can find an inverse. So that is the determinant. So it's definitely worth taking a look at the textbook for that explanation, especially if you are prepared with a bunch of algebra. Yeah, prepared for a bunch of algebra, which is, with what it's going to require. Before we do the n by n case, let's collect a little bit of notation here. Sure. So if A is equal to the same thing we just saw, A, B, C, D, E, F, G, H, I. So we'll call capital A11 the 2 by 2 matrix we get by eliminating the first row and first column. So this is the 2 by 2 matrix obtained by deleting row 1 and column 1 from A. So A11 is E, F, H, I. And then similarly, A1J is just going to be the 2 by 2 matrix we get by deleting the first row in jth column. Two by two matrix obtained by deleting first row in jth column. from A. Okay, so then what? If with this new notation, the determinant just becomes A times the determinant A11 minus B times the determinant A12 plus C times the determinant A13. And now we can sort of see how this is likely going to generalize. We should keep on alternating back and forth between plus and minus. We should go across the first row of our n by n matrix and picking up these smaller determinants the entire way. And that's what I got written down here. The n by case is completely analogous. We'll build up the n by n determinant from the n minus 1 by n minus 1 matrices obtained by deleting row 1 and column j, taking the determinant, weighting by a1j, and between adding and subtracting. So let's write this down. For n bigger than or equal to 2, the determinant of an n by n matrix A, which we can write as aij, or here we have written down a11, a12, all the way up through a1n. So the next one would be a21, a22, a2n, and so forth, all the way down to an1, an2, ann. The determinant is just going to be, we'll pick weights from across this first row, and we'll hit that with the determinant of the n by 1 minus n minus 1 by n minus 1 matrix we get by deleting that row and column. So it's going to be a11 times the determinant of big A11 minus A12 times the determinant of big A12 plus da 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 da. And now we've got to do plus negative 1 to the n plus 1, which just means we've been alternating back and forth, back and forth, back and forth. A1n, determinant big A1n. Okay, yeah, the like negative 1 to the n is just to make sure that we end up with the same, that if there's a odd number of rows and we end up adding at the end, or if there's an even number of rows, we end up subtracting at the end. That's all that's doing. Okay, if this was not that concrete and too abstract, don't worry, let's do an example. Make this whole thing make way more sense. To avoid writing a million little debts everywhere, we're going to use like absolute value bars to mean the determinant of a matrix. Let's make that one a little straighter. Oh, like that. So the absolute value of a big matrix, that just means its determinant. And that'll make our life slightly easier when we have a million determinants to compute. Okay, so we've got a 4x4 matrix. We're gonna roll up our sleeves, which is actually not so bad right now. We'll roll up our sleeves and compute its determinant. So we know that the determinant of A should be 1 times that determinant. So it'll be 1 times, we're using the absolute value to mean determinant, 1, negative 1, 0, 1, 0, 0, 0, 5, 6. Right, that's the 3x3 matrix we get by deleting the first row and column. And then we go -2, because we're looking at this thing now. We should eliminate that row and column, and that'll give us a 3x3 matrix whose determinant we want. So that'll be 0, 1, 2, negative 1, 0, 5, 0, 0, 6. Plus 3 times the determinant of the 3x3 matrix we get by deleting the row and column that 3 lives in. So 0, 1, 2, 1, 1, 0, 0, 0, 6. And finally, -4 times 0, 1, 2, 1, 1, 0, negative 1, 0, 5. That 0 is looking 6-ish. Let's correct it. There we go. Okay. So now we need to compute each of these expletive determinants. So we need to continue rolling up our sleeves and continue grinding out this determinant. So let's do this one at a time. So we know the determinant of 1, negative 1, 0, 1, 0, 0, 0, 5, 6. This one we can do by, because we know what the 2x2 determinant is concretely. So this is going to be 1 times the determinant of 0, 0, 5, 6 minus -1 times the determinant 1, 0, 0, 6 plus 0 times, it doesn't matter what we have here, but for formality, we'll say that, right? Okay, so this looks like 1 times 0 times 6 minus 0 times 5, so that's 0. This is plus 1 times 6 minus 0 times 0, no problem there, plus 0 times plus 0, right? 0 times 5, sure, if that makes you happy. Okay, so this whole thing is just equal to 6. Let's do the next one. 0, -1, 0, 1, 0, 0, 2, 5, 6. Make this more legible. Oh, okay. So it'd be 0 times 0, 0, 5, 6, minus -1 times 1, 2, 0, 6, plus 0 times 1, 0, 2, 5. Do you have to write down the zeros? I can't stop you, I guess. 0 plus 1 times 6 minus 2 times 0 plus 0 times 1 times 5 minus 0 times 2. So this is also 6. Okay, couple 6s. It seems funny, but all right. The next one was the determinant of 0, 1, 0, 1, 1, 0, 2, 0, 6. I'm sure that's what I had up here. Yeah, good. Okay, so this becomes 0 times the determinant of 1, 0, 0, 6 minus 1 times the determinant of 1, 2, 0, 6 plus 0 times 1, 1, 2, 0. Okay, this is 0. This is minus 1 times 6 minus 0 times 2. It's plus 0, so this is -6. Okay, they're not always these numbers. And then finally, we want the determinant of 1, 0, 1, -1, 1, 1, 0, 2, 0, 5. 5. Okay, this is 0 times 1, 0, 0, 5 minus 1 times 1, 0, 2, 0 plus -1 times 1, 1, 2, 0. Okay, so that's 0 minus 1 times 0 minus 0 times 2. I'm sorry. I've made a mistake up here, right? We're looking at this -1, so we should eliminate those two. So 1, 2, 0, 5. So this is 1 times 5 minus 0 times 2. And then that looks right to me, plus -1 times 1 times 0 minus 1 times 2. Okay, so this is giving us nothing. 5 minus 0 is -5. And this is plus 2 is -3. Okay, so then our original determinant is 1 times 6 minus 2 times 6 plus 3 times -6 minus 4 times -3. 1 times 6 minus 2 times 6 plus 3 times -6 minus 4 times -3, which is -12. Ooh, okay, so that was our big old 4x4 matrix determinant through computation. Yeah, I'll see you soon for the next video. Take care, everybody.